Hey, and welcome back to AP Calculus AB. We're on topic for our applications of derivatives. Today's lesson actually has two parts to it. Although the title is Local Linearization and Tangent Line Approximations, we're actually going to start with the idea of interpreting units. And I'm never quite sure where to put this, and I think it fits in pretty well here because a bunch of our local linearization will be application problems. We actually saw interpreting units and related rates, but I never have a specific day where I go through problems where they're like, what does this mean? What are the units? How does it work with derivatives? And so since tangent lines are pretty commonplace, we've done them a bunch, and this lesson itself isn't too hard, I think it's worthwhile taking some time to talk about units. So I have 9 problems on this first page for you, some multiple choice, some short answer. You're going to want a calculator. You're actually going to need a calculator a bunch today. I've mentioned probably every day for the rest of the semester you'll want one. Some of these require a calculator, some do not. And I'm going to go ahead and probably work through a few of these. However, a lot of them are pretty logic-based, and I think once you see how to set them up, I would really suggest just pausing me, trying them all, and then checking your answers at the end. So I'm going to go ahead and scroll down to where I set these up to have more room. You'll probably want a separate piece of paper. Let's get to it. Let P of t be a function. Now, whenever I see P of t, and they're going to ask us to interpret dp dt, I would really suggest that you remember what P of t is. Now, the problem that I have with this notation is that the AP exam is not very consistent. In particular, I would actually prefer that they wrote P equals a function of t, so that you can see that P is the output, t is the input, and F means things are happening to t. And in particular, sometimes it helps just to make up your own equation. I mean, I don't know what the equation is. Maybe it's, t squared plus 2t, something like that. Whatever. Okay. Now, let's go ahead and continue the problem, where P represents the size of a population at time t in years. Interpret the units of dp dt in context of the problem. So there are a few ways to approach this. My favorite, though, is to say, how can we create dp dt? Well, to create dp dt, of course, we would have to take ddt of each side of this equation. Now, going a little bit further here, and I'll keep my equal sign maybe in the middle, the derivative of time, and again, I made this equation up, it's not really relevant for this, is going to be, it's going to stay time. This is our input, and our independent variable is never going to change units. So if I went, this is 2t plus 2, my input units are time in years. Easy enough. My output units, though, do change. And the easiest way to figure out your output units is to write what's going to happen, so it becomes dp dt, and then put the units after it. The change in P units. Well, the change in P is, well, P is the size of the population, right? So this is going to be the size of the population as what changes? Well, the change in time, so over years. So how do we interpret dp dt? dp dt measures how the size of the population changes as the years change. Realizing that when you take a derivative, there's always going to be a set of 2 units here, or more than that, as we'll see later on. And it's going to be the output units over the input units is really, really important. So let's try another. The level of water in a tank in gallons over some amount of minutes is given by g of t. Again, g is the output, and it's created by doing some function or some function acting upon t. All right, what's the meaning of dg dt? Well, in order to do this, I have to do d dt of each side. Okay, and I'm not actually making up my own equation this time. I get dg dt, and we get the units. The change in g. G is the level of water of the tank in gallons. So this is the change in gallons over what's time? Time is minutes over the change in minutes. So dg dt, and then if we write the other side, ddt of f of t, we just write as f prime of t, right? Showing that dg dt is going to be, again, some function acting upon t. So dg dt measures how fast the gallons are changing as the time moves on. Seems pretty easy so far, and if you're feeling comfortable with this, you're definitely welcome to go on and try the next few. All right, h is differentiable. That means we're able to take the derivative everywhere. It's a differentiable function of t. So they're giving us h of t. And so again, I like to rewrite it as h is some function of the input t. What is the following best interpretation of h prime of 24? Well, h prime means the derivative of h with respect to t. So ultimately, in order to get an h prime out of here, so h prime equals some stuff, then what we need to do is we need to take d dt of each side. It's always assumed that whatever the input variable is, that's what you're doing d dt with respect to on each side. Okay, so this is d dt of h. So then this becomes, and I should have done better with this, apologies, it becomes dh dt is equal to the derivative, so f prime of t. All right, so what is dh dt? Well, don't forget first that dh dt is the same thing as h prime. Okay, and in terms of units, the top of our fraction, the change in h, what is h? It gives the temperature in degrees. H is a differentiable function of t that gives the temperature in degrees. Which of the following is the best interpretation? So this is pretty tricky here. My guess is that, strangely, t stands for time. It says h is a function that gives the temperature. So that is the output. It doesn't take a temperature. So h here is going to be the change in temperature in degrees Celsius. So what is t? T, and this should be a capital, is our time. Okay, so this is our change in time. All right. Oh, and there they tell us. They tell us t is hours. I wish I could read a little bit better. Oh, silly me. Change in hours. All right. Now this one gets a little more specific because now they're saying, what is h prime of 24? Well, 24 is an input, and it's saying the time is 24 hours. Now we need to remember what we originally called a derivative. The original definition of our derivative was an instantaneous rate of change. And it's so important to remember that a derivative measures a single point's slope or a single point's rate of change on a function. It doesn't measure an interval. It says right here. In this case, right exactly at 24 hours, what is happening. Okay, well, let's take a look at this, and let's eliminate a few of these options. The average rate at which the temperature changed during the 24-hour, no, it's not an average. It is an exact rate. Okay, does it measure the change in temperature over the first day? Well, let's look at this, right? H prime of 24, let's give it an answer. Okay, so if I wanted to give this an answer then, let's say the answer is 12. Well, 12 would be 12 degrees changed over hours, right? Over maybe 1 hour, something like that. So this is telling us how fast we're changing at the 24th hour. So is it the change in temperature during the first day? No, it's not during an entire day. Is it the change in temperature during the 24th hour? Probably not, but let's come back to that. Change in temperature, it can't be that. If temperature is going to change, then the units are just going to be in degrees Celsius, right? If you're at 40 degrees Celsius and then you're at 10 degrees Celsius and you wanted to see the change, well, the change is 30 degrees Celsius, not Celsius per hour. So that one's pretty tricky. Last two, the rate at which the temperature is changing during the first day. The first day incorporates 0 hours, 1 hour, 2 hours, 3 hours, too many hours. We are doing at 24. So the rate at which the temperature is changing at the end of the 24th hour. Really, it could have been at the beginning of the 24th hour, but it needs to be at something to do with that 24th hour, and we're good to go. And notice rate. Rate is always a giveaway for a derivative. Let's try a few more. I think you'll need your calculator for this one. A cup of tea is cooling in a room that has a constant temperature of 70 degrees Fahrenheit. If the temperature of the tea changes at the rate R of t equals this weird thing, then what is the value and meaning of R of 3 and R prime of 3? Okay, well, we know, of course, that R is some function of t, and in particular, we know the function of t is this guy up above, t, because there's t and it's cooling. You get it? Okay, so we end up here. And they're giving us some units here too, I think. So they're telling us that R is in degrees Fahrenheit per minute. And that makes things a little bit trickier. So if we're looking at units, we know that R is already in degrees Fahrenheit per minute. And then so they're asking us, what is the meaning of R of 3? Well, 3 is an input, so that's a t value, and in this case it's in minutes, so this is going to be at time equals 3. So actually I think we can even write what's happening without having to do any math here yet. So at t equals 3 minutes, right at the third minute, right, the temperature, this is our output, right? The temperature is changing by, and I did not do well here in terms of space, oh well, by something degrees Fahrenheit per minute. So why don't we take a quick second, use our calculator. This problem has no calculus involved, which is exciting, at least so far. Now, why might it not have any calculus involved? You might notice that our units are already in degrees Fahrenheit per minute. That's a rate. So technically capital R is already a first derivative. So I'm going to just go ahead and pull up my calculator really quickly. I think I can use that and take a look at both at the same time. I'm on my scratchpad screen, so we have negative 6.89. And then don't forget, oh, I have to pick. That's funny. Negative 6.89. Don't forget that when we use e, we don't use this keyboard e down here. That doesn't mean our e to the power. We actually need to use this e button. So it's e to the power of negative 0.053, and then times what? Well, we're inputting 3, aren't we? And then let's see what we get. My guess is I should have, oh no, they gave it to us. That was so nice. Negative 5.877, always going at least 3 decimal places. Negative 5.877. Now, some people will say, well, wait, how come you said changing and not decreasing, right? They're telling us that the rate is negative, so negative degrees Fahrenheit per minute. I mean, if you think about the problem, the T is cooling. Couldn't we have said that the temperature is cooling by this amount? And actually, no, because if you say that our temperature is cooling by a negative amount, cooling by a negative amount is like a double negative, and that actually means that the temperature is increasing. I think what you might have been trying to say is you could have said is cooling at a rate or by positive 5.877, and that's okay. I'm a big fan of the word changing because changing can either be negative or positive, and then you don't have to worry about the sign. If you try to involve these fancy words like cooling or increasing or decreasing and you get the wrong negative, you end up missing the problem, which is a bummer. All right, let's go ahead and continue through because there's actually one more thing to do in this problem, I think, and the one more thing to do in this problem is the other part of the problem. It says to find r prime of 3. So r prime of 3 here, what are we doing with this guy? Well, to find r prime of 3, we need to take a derivative. We'll get back to that. I think, though, we should probably talk about units, right? If this is r, so currently r is in terms of degrees Fahrenheit per minute, degrees Fahrenheit per minute, and I want to do d dt of this to get me to r prime, then think about what happens. It's going to be dr, which is already in degrees Fahrenheit per minute, divided by dt, and time is in minutes. So I think my units here are going to be degrees Fahrenheit per minute per minute. And really, you'll find as you take derivatives, what ends up happening is whatever the independent variable just tacks itself onto the denominator. If it makes you happier, you can also write this as degrees Fahrenheit per minute squared. And maybe that's easier to see the pattern. When you take the derivative again, it'd be cubed, and then to the fourth, and so on and so forth. I actually like writing it better this way because, well, we'll see in just a second. Let's go ahead and find the value of r prime of 3. To find r prime of 3, we're going to go back to that calculator. And the reason we're going back to the calculator is because we're going to have the calculator do all the work for us. We don't want to forget our cool uses of our calculator. And this is an accepted and actually expected use of our calculator. This is my function up here. So I'm going to go Menu, Calculus, and then Derivative at a point. Okay, derivative at a point, variable, x is fine. What value are we plugging in? 3. What's my equation? Negative 6.89 e to the power of negative 0.053 times, and not t here, because I picked the variable x. You could have picked t and then just used t all the way through, but this looks fine to me, and we figured out 0.311. So the nice part about doing it this way, 0.311, is we didn't have to do any math, right? Don't forget that your calculator is extremely powerful. So r prime of 3 equals 0.311 units, degrees Fahrenheit per minute again. How do we interpret this? Well, what does r prime measure the rate of change of? R prime measures the rate of change of r. And so this is telling us how fast r is changing. And in fact, if you wrote it like this, it actually might make more sense, where we move the 0.311 to the top of the fraction and then put a 1 on the bottom. Does that help you? Right? At a time of 3, r, which is already the rate that the cup is cooling, is changing by 0.311 degrees Fahrenheit per minute per every 1 minute. So in real life, we'd say every 1 minute that goes by, the rate that the cup is cooling changes, actually increases by 0.311. So the cup is starting to cool faster and faster as we decrease, and that's somewhat interesting. However, if we're looking at this, you should probably write out your interpretation, and I'm out of room, but we'll try anyway. So at t equals 3, r of t is changing, right? Because r prime measures the rate of change of r. R of t is changing by 0.311 degrees Fahrenheit per minute, and that would be fine. All right, let's move on through, and the rest of these will go a little bit faster. P of 0 equals 1500 gives the amount of deer in a forest at time t equals 0 years. Interpret P prime of 2 equals 27. So we already know that P is the amount of deer. Okay, if we do d dt of P, then we have dp dt. Okay, P was already amount of deer, and t, this time right here, is years. So if we wanted an interpretation of P prime of 2 equals 27, we would say at, not over, at a time equals 2 years, the deer are changing at a rate of 27 deer per year. And see how easy it is once you have the units there? You just tack it on to whatever the derivative is, and you're just fine. Moving through. The velocity v in meters per second of a certain type of wave, yeah, we're probably thinking like waves in water, right? Is given by v of h equals blah, 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 where h is the depth in meters of the water. What is the rate of change of the velocity of the wave with respect to the depth of the water? They already told us the depth was h, so they want the rate of change of the velocity. So we want dd something of velocity, okay, when the depth is 2 meters, so evaluated at h equals 2. dd what of velocity? They said with respect to the depth of the water, where h is the depth. So it's ddh of this guy. So what does this give us? Probably should have done better with this. So we have dv dh equals, and we do need to take the derivative of the other side too, 3 times h to the 1/2. And yes, your calculator could do all of this for you, but I already started, so too late. dv dh equals, and then the 3 is a constant, 1/2 comes down, h to the negative 1/2. You could multiply by the derivative of the inside, but because there's a dh, it just becomes 1. And so I think we're looking at 3 over 2 times the square root of h. Let's look at units really quickly. V is on top. V is already in meters per second. And h is the depth in meters. Meters per second per meter. So one way to read this is Well, actually, we should probably plug in the value. I think that'll make this easier because they asked when the depth is 2 meters. So they're asking us to find dv dh h at 2 meters, and that's going to be 3 divided by 2 times the square root of 2. Okay? Thinking of this as 3 over 2 square root of 2, keeping the units, meters per second, per meter, means that every 1 meter you move, the velocity changes by 3 over 2 square root of 2 meters per second. Moving on through. These last ones are multiple choice. You should probably try these on your own. You guys don't have a number 10, so just 7 through 9. Once you finish trying them, get back to me. All right. P of t, population of the world, that's got to be P, in billions of people, where t is the number of years since January of 2010. So p prime of 1. What's the interpretation? Let's start with p prime. The way we get p prime is we take the derivative of p with respect to t, so that's going to give us dp dt. And in terms of units, p is the population in billions. Okay, and dt is in years since 2010, isn't it? That seems right. Okay, so they're asking for p prime of 1 equals that number. So 1 year after January 1st of 2010, the population is changing. That is changing is our big buzzword here. Is changing at 0.076. And again, I'm just going to keep this as population in billions per every 1 year, and I think that should be fine. So let's see, how do we do here? On February 1st, I think it's number of years, not number of months, so that one's out. January 1st, 2011, that looks pretty good. The population of the world was increasing at a rate of 0.076 billion people per year. That sounds a lot like ours. Let's come back to that. On January 1st, 2011, good so far. The population of the world was? No, we found a rate. The rate is not the actual amount, it's the population. From January 1st, 2010 to 2011, there's no average rates. We're talking derivatives. Derivatives are instantaneous at a specific time. When the population of the world was 1 billion people, the population of the world was increasing at 0.76 billion people per year. Ooh, they're trying to trick us here. So this one would be if you took the next derivative. The second derivative here, like so, would take the rate of change and divide it by years. So the second derivative will measure the population in billions of people per year, so how fast that population is changing as years go on, or how fast the rate of the population is changing as years go on. That's what this is saying over here. So that's not what we found. We found the first derivative, got to be B. 8. Height above the ground, differentiable function, so h a height, t is minutes, so they want h prime, so we're really looking for dh dt here. Dh dt dh is going to be the height in meters. It's the height above the ground in meters, I guess. Height in meters above the ground. Okay, over our change in time here. So our change in time, good interpretation. What was our time in minutes? Awesome. Okay, so they gave us h prime of 7.5. So we know that this is a time, and this, because it's an h prime value, is really saying 15.708 meters above the ground per every 1 minute. So what is that telling us? It's telling us as every minute goes by, at a time of 7.5, the person's height above the ground is increasing by 15.708. I know I said increasing instead of changing, but it's positive, so it's pretty easy to work with. So here we go. The Ferris wheel's turning at a rate. I don't think so. Well, they didn't tell us about how fast it's turning. They just told us about the passenger's height above the ground. Passenger's height above the ground is increasing by 15.708 meters per minute. When the passenger is 7.5 meters above the ground. Wait, that's not 7.5 meters, is it? That's in time. That's minutes, so that one's out. Passenger height above the ground is increasing by 15.708 meters per minute. 7.5 minutes after. Yeah, this is in meters per minute, and it is 7.5 after. It's got to be D, but let's look at E. The passenger is 15.708 meters. No, this is meters per minute. Cool. And that one's out. Last one, the crazy problem. A tire is leaking air, has an initial air pressure of 30 pounds per square inch. And actually, that's pretty good. A lot of your tires, they usually say your tires should be like between 30 and 34 psi, right? When you go to fill up your tire, you should look on the inside of your door. It'll tell you how many pounds per square inch. And you go to the gas station and you put in your little measurement. It says, oh, your tires are at 24 pounds. You're like, oh, that's not good. Then you fill them back up. That's essentially what's happening here. We have the function T equals f of p. And this is where things get wild. Models the amount of time, T in hours, it takes for the air pressure of the tire to reach P psi. And the reason they're doing this is because this is leaking air. So essentially what's happening is you are starting at some psi, and you're going to input a psi. Let's say you started at 30, and then you were like, I wonder how long it's going to take my tire to drop down to, say, 20 psi. So you input 20, and it'll tell you, here's how long it will take for your tire to drop. Somewhat useful. As we go through, we need to take the derivative with respect to p. And that's why this problem is so weird. People see that t and they're like, ooh, we must be taking the derivative with respect to t, and you're not. You always take the derivative with respect to the independent variable. So f prime of t, or if you wanted t prime, right, the derivative of this is given by dt dp, which is going to be the time in hours per the air pressure in psi. So if you read this straight down, our units for T prime are hours per psi, right? Reading straight down. And that is a really tricky question. You're like, psi per hour, we're so used to time being in the denominator, it's something per hour, but we're not doing it per hour, we're doing it per psi. Every psi changes the time. Tricky, tricky, tricky. All right. Well, at this point, we've taken a long time to go through that. Hopefully you skimmed through quickly because we definitely have more to do today. So let's get to it. If you're given the following two graphs, describe how the shape of the graph will appear to change if you zoom in indefinitely on the given point or cusp. So we're going to go ahead and zoom in on the point here, zoom in on the cusp here, and we're curious what will happen. Okay, how will the cubic looking graph, that's my first graph over here, right, look if you zoom super far? What about the cusp? What sort of slope would the tangent line have in the second graph at the cusp, if you could draw a tangent line there? Okay, so try that first, and then we will go back and go through this a little bit more in depth. All right. Local linearity is a concept we've heard of before, and we're going to go much more in depth with that today. It's the idea that a smooth curve, also sometimes known as a differentiable curve, right, appears straighter when you zoom in. So no matter how curvy this is, if you zoom in far enough, it will look quite straight. Now actually, this is one way we defined a tangent line early on. We said if the curve and the line look parallel around the point of tangency, then they're tangent. So we're going to go ahead and do a quick look at local linearity just using a nice Desmos example that I have prepared for you. And I have approximate graphs of each of these, though at different x values. It doesn't have to be perfect, and it won't be because I didn't want to be. So the first one we're going to do is look at that differentiable function. I should probably do this and zoom in home. There we go. So this is my cubic with my tangent line going through, right? Nothing too bad. I just created my own stuff here. Here is my point of tangency, and look what happens as we zoom in really, really close over here, right? We can see these lines, which originally didn't look parallel, but as I zoom in farther and farther, A, it looks like we have two parallel lines here, and B, lines, not a curve. In fact, if I gave you this, you'd probably be hard-pressed to decide which one was the curve and which one was the tangent line. This is the idea of local linearity. As we get close, a graph looks linear. Also, as we get close to a real tangent line, the graphs look parallel. Okay. Notice this is still a tangent line even though it crosses through somewhere else because we built the tangent line based on the slope over here. It doesn't matter if it touches other pieces. Let's look at that cusp. All right, and I'm going to play around with this quickly. I'm going to go ahead and get rid of my tangent line for a quick second. Here is the cusp. And let's get rid of that point too. There we go. All right, as I zoom in on the cusp, you'll notice that if I keep zooming in on the cusp, you're never going to get that linearity here, right? Our cusp is still always going to come to a sharp point. It's never going to ever end up looking linear at the cusp. Sure, I mean, these guys look pretty linear, but this never looks linear. This always looks like a point instead of a smooth curve. So that's a good idea that this will not have local linearity, or another way to say it is our function is not differentiable at that point, because no matter how far you zoom in on the point, it never starts to look like a line. It always looks like a point, sharp point, something like that. Now the second question was asked was, what does a tangent line look like here? So I have a cool tangent line prepared for you. And you'll notice as I move this guy, the tangent line shows you the point where the line is fixed. And anywhere you zoom in over here, you do get local linearity. Eventually these two start looking parallel to each other. But what happens is I move this close to the cusp, right? Pretty good. And we have a pretty negative slope here, right? More negative, quite a negative slope. Up, and then I get to -2 and then it disappears. And then we go to the other side. Oh, we're back, but now we have a very positive slope. Can you see what this tangent line is approaching slope-wise as we get closer and closer here? Right? It looks like my tangent line is getting close to vertical here. And if I wanted, let's go really, really close. Let's go -2.01. There's my tangent line. What about 0.001? Ooh, that's super steep. 0.001? We're still very, very steep here. And you'll notice as I zoom in, we do have that nice linearity here, but you still see that point all the way up above. And it's never perfect up there. And so eventually what ends up happening is if you write a tangent line at the cusp, the tangent line is vertical, which means the tangent line has no slope. And the reason we don't write a tangent line is because it's no longer a function. It'd have to be x equals to go straight up and down, not y. We wouldn't be able to have a slope here. All right, so we have that cusp, nothing too bad. Now, what the heck are we doing today? Well, we're going through the idea of linear approximations. So let's imagine we're given some sort of function. In this case, I'm going to use the function f of x equals e to the x, and you don't have a calculator. Well, linear approximations give us a pretty quick way to calculate values for f of x, for e to the x in this case, without a calculator. And they don't give us a perfect answer, but they give us a close answer. And they do that by creating a tangent line, which we've always called t of x in the past, or sometimes you'll see these linear approximations called capital L of x, where they use L to stand for linear approximation or linearization of f of x at a specific point. Essentially what we're doing is we're saying e to the x seems intimidating, so we're going to create a line which is very much not intimidating, and close to wherever our line is tangent, our line is pretty much the same as e to the x. Right? So let's go ahead and take a peek at what the heck I'm trying to say. All right, e to the x. This graph should probably hit home. There we go. And I have a point on there as well. Nice. Okay, now if I create a tangent line here, I'm going to create a tangent line right at that point 0, 1. Okay, and then I said, okay, without a calculator, I would like you to tell me what the value is of e to the 0.5 power, e to the 1/2. I'd like you to tell me what the square root of e is. Could you do that? Well, e is 2.718, the square root of 2.7, so some of the square root of 3, weird, awful decimals. I'd have some trouble with that. I know it's smaller than 2.718, but I'm not sure how much smaller. So let's look at that point. That point is right there. Then let's look at the point on the tangent line that also has an x value of 0.5 right there. Are those 2 points pretty close to each other? Let's see. They look pretty darn close to me. In fact, let's compare the two decimals here. 1.5 versus, well, real struggle at this point since it does not want to give me the exact decimal here, but that's fine. Close enough. Versus 1.64. Are 1.5 and 1.64 pretty close in terms of ballpark range? I feel like they are. They're what, 0.15 away, right? 15 cents if you wanted decimals, which is not a lot. So if I said I wanted you to approximate the square root of e, do you think I'd be content with an approximation of 1.5 versus 1.64? In some cases, sure. In other cases, you might say, no, those are still too far away. You always have to be accurate to 3 decimal places. I hate that. Well, then you're not going to like today, because this is essentially what we're doing. We're saying we have some curve, and since we don't have a calculator, which strangely you will have a calculator at some point, we won't be able to figure out this value. But by knowing our tangent line, we can at least approximate what the value is close to. And I think we could all agree that 1.64 is decently close to 1.5. Now, if you want to get a better approximation, then you have to take Calc BC with me next year, because then we're going to learn how to write a better tangent function. And instead of a line, I'll keep that up there, you have a curve. And now look at those 2 points. Oh, this one is 1.68, and this one is 1.64. Oh, now it's working. Are those pretty close? Well, I bet both of us, everyone here, would probably say, yeah, they're 0.04 apart. They are extremely close. And so next year, a lot of the focus goes into how do we make this tangent line better or do a better job of approximating this. And I did this with just 4 terms here, right? 5 terms, sorry. 5 terms. I could pretty quickly plug in 1/2 to all of those x's, do some math, and come out with this value, which is now not working again, very exciting, with this value, this 1.68 value, and say, woohoo, I was able to do that without a calculator. This year we only know tangent lines, but it's okay. It'll work out just fine. So let's get to an example or two. Create a linear approximation to f of x equals the square root of x at x equals 4. All right, linear approximation, just think tangent line, right? There's nothing too hard. We know how to make tangent lines. I'm going to use L of x today instead of T of x. They mean the same thing. You can pick whatever letter tickles your fancy, right? So we have L of x, the linear approximation, is going to be found by doing f prime of 4 times x minus 4 plus f of 4. Cool. Okay, zooming in a bit, we know that f of x is the square root of x, which is x to the 1/2. And we also know that f of 4 is the square root of 4, which is 2. Second, f prime of x, we'll use this guy over here, 1/2 x to the negative 1/2, which is 1 over 2 square roots of x. So then f prime of 4 is 1 over 2 square roots of 4, 1 over 2 times 2, which is 1/4. Final linear approximation, we end up with 1/4 times x minus 4 plus 2. Cool. Now, it suggests to use the table feature of your graphing calculator to compare the y values. I'm going to do this visually. Tables are cool, but I find myself not using them too often. Totally up to you, but if you have your graphing calculator, now's a great chance to go ahead and graph these two. I'm going to do it on Desmos just for clarity, but you should use your calculator. The more you use your graphing calculator, the more you'll be prepared for the AP exam. So I'm going to go ahead and we're going to get rid of this guy and look at our 2 equations. Y equals the square root of x and our tangent line. I wonder if I can do L of x on here. Sometimes it's okay, sometimes not. And that was, I think, 1/4 x minus 4 plus 2. Does that seem right? Yeah. Hit the home button. And let's look at that point of tangency. The point of tangency was 4, 2, wasn't it? Okay. So if you look at this graph with my current zoom, you might be asking, well, how close is close? And that's ultimately up to you. I mean, I would say that the tangent line, really from like x equals 2, right around here, all the way over to x equals 6 is pretty much indistinguishable. I bet any point that's on my tangent line will pretty much have the same y value as my square root curve. But then we start to get a little further away, right? If we compare over at like 12 here, 12 on my tangent has a value of 4. 12 on my square root has 3.4, so it's like 0.6 off. That's not super far off. But of course, the further out we go, the further off we get. And then over here, the furthest we're ever off is 0, 1 versus 0, 0. We're off by 1 here. So it ultimately is up to you of how far away you think we're allowed to use this tangent line, right? If I said, I want you to calculate the square root of 5, you could say, no. Instead, I'm going to go to 5 on my tangent line. I'm just going to plug in 5 and get 2.25. as opposed to having to figure out a way to calculate the square root of 5 and get 2.23. 2.25 versus 2.23, those are pretty darn close to each other. So I think our tangent line would do a good job approximating 5, but it'd probably do a pretty poor job of approximating, oh, I don't know, 40, right? You'd be pretty far off there, or so on and so forth. Yeah, let's jump back. Without a calculator, approximate the value of the square root of 3.9. Well, here we go. To find the square root of 3.9, remembering that f of x is the square root of x, then what that meant is we found f of 3.9, which is, of course, the square root of 3.9. How does that help? Well, we are going to approximate f of 3.9. But to do that, we need to remember that our input value was 3.9. That throws some people off. The way we're going to do it is instead of plugging 3.9 into the square root of x, we're going to plug 3.9 into the equation that's very close to the square root of x, which is, of course, our linear approximation. So I'm going to leave a little space in front because we're going to go back to that. I'm going to evaluate my linear approximation at 3.9. So it's 1/4, 3.9 minus 4 plus 2. And we'll work on down this way. 1/4, 3.9 minus 4 I think is negative 0.1. 1/4 and negative 1/10, right? We read this as 1/10, so we write it as a fraction 1/10. And then we multiply, this is negative 1/40 plus 2. And then don't make this too challenging. You're at 2 and you're subtracting 1/40. That's 1 and 39/40. Cool. Now, as a reminder, we were trying to approximate f of 3.9, so the right way to put the work on here is to say that f of 3.9 is not equal to the linear approximation. They're not in the same spot. They are approximately equal. So you do need to start with that approximately and say we're going to find f of 3.9 approximately by using the linear approximation, which is exactly equal to 1 and 39/40. Okay. Then the question says, is your approximation less than or greater than the actual value of the square root of 3.9? Well, 3 ways to approach this. Way number 1 is the way we're not going to do it. Way number 1 is, cool, you need to actually take the square root of 3.9 on your calculator. But this would never be a calculator active question because then you would just plug in square root of 3.9, compare it to this, and see what you did. In fact, we should probably try that really quickly. And I'll pull up my other calculator. So we had 1 and 39/40, the dumbest notation in all of math because it means 1 plus 39/40. We get this. They say it's that, but I don't want that. I want the approximately, please. 1.975. Compared to the actual square root of 3.9, 1.9748. Look how close that is. Those are almost the same. And it shouldn't shock you because 3.9, and this is the second way we can do it, is by looking on our graphing calculator. 3.9 is right next to 4. And so if you zoom in and go right next to 4, I mean, I still can't even tell the difference, and we're at approximately 3.9 right here. They're like right on top of each other. So since the tangent line's in the same spot as f of x, then, I mean, yeah, of course, they're going to be a pretty darn good approximation. But what happens if you either A, get a graph you don't know the shape of, or B, I guess you don't have a calculator? How do you know if an approximation is less than or greater than? Well, let's jump back to this curve here and think about the location of the tangent line. Would you agree that for every point on here, it always hates my pen, but that's fine. Would you agree that for every point on here, the tangent line's y value is above the red graph, the square root of x's y value? For every single point, except right at that point, they're equal. But for every other point, the tangent line is always above. Well, what property of f of x equals the square root of x, of the red graph, what property is causing the tangent line to be above? This is actually another way we originally defined tangent lines. We defined tangent lines as either always being above or below, and I guess that's not true. We didn't define tangent lines. We defined something else. We said if the tangent line is always above a graph, then that graph is something. Well, the property of the red graph that causes the tangent line to be above it is that the red graph is concave down. So the concavity is how we can tell if this is going to be an over or under approximation. So let's look. We already have f prime over here. Let's find f double prime. So we know that f prime of x equals 1/2 x to the negative 1/2. Let's do f double prime. Okay, negative 1/2 comes down, x to the negative 3/2. And cleaning this up a little bit, it's negative 1/4 times 1 over x to the 3/2, or continuing out, negative 1/4 times 1 over the square root of x cubed. Well, let's break down the second derivative. If we have negative 1/4, that is, of course, always a negative value, times 1 over the square root of x cubed. Well, knowing what you do about the square root always has to be positive. That's why it's only in the first quadrant, right? It stops at 0, 0. So if the x's are always positive, then isn't this always a positive? And so I think you could probably convince yourself that the second derivative, no matter what x value you plug in, will always be negative. So what does that tell you about f of x, the original function? Well, it tells you that f of x is concave down. So I would just draw a quick concave down graph. And then think about your linear approximation with what I did in purple. Any linear approximation is going to be above or an over or greater than approximation than the actual value. So how do you justify this? Our approximation here is greater than the actual value because f double prime is negative for all values, and thus f is concave down. So we're going to go ahead and try one or two more of these together, and then you guys are actually going to do the rest on your own, and I'm just going to post the solutions here so I don't just sit here and talk your ear off. So let's try 1a, we'll do 2a, and then call it good. Find the local linearization for this. They're just asking for a fancy tangent line. We got this. L of x equals f prime of 3, x minus 3 plus f of 3. Okay, so we need f of 3. That one's not too hard. I'm going to start with f of x, actually, and I'll write this guy twice. F of x is going to be 1 over x minus 1, or if you want, x minus 1 to the negative first, and that will become important in just a bit. However, f of 3, hopefully you can see, plug in 3 here, 3 minus 1 is 2, so we get 1/2. F prime of x, well, I'm not going to take the derivative of this. I'd have to use the quotient rule there, and that seems like overkill. I am going to take the derivative of this. That seems way easier. Negative 1 comes down, keep x minus 1 the same to the negative second, times the derivative of the inside chain rule, but the derivative of x minus 1 is just 1. So I think we get negative 1 over x minus 1 squared. All right, little mental math here, but I think you guys are up for it. If we substitute in 3, we get negative 1 on the top. 3 minus 1 is 2. 2 squared is 4. Final linear approximation, aka a tangent line, we get negative 1/4 times x minus 3 plus an f of 3, I think was 1/2. Nifty. Use L of x to approximate f of 2.9. So clearly our input here is x equals 2.9. So let's go ahead and approximate that. The way we approximate it is we say that f of 2.9 is going to be approximated by L of 2.9, which is exactly equal to negative 1/4 of 2.9 minus 3 plus 1/2. All right, so we end up getting negative 1/4. This is going to be negative 0.1, negative 1/10 again, plus 1/2, 1/40th, plus 1/2. Ah, common denominators. Who invited you? Times, let's see, to get to 40, I think we have to multiply by 20, don't we? So that's 20 plus 1. I'm getting 21/40ths. Cool. Part C. Is L of 2.9 an over or under approximation? Justify your reasoning. Well, let's find the second derivative. We already found the first derivative, right? That's over here, and I'll rewrite that so we don't forget about it. The first derivative was negative 1 x minus 1 to the negative second. So the second derivative is going to be 2 times x minus 1 to the negative third, or 2 over x minus 1 cubed. This is something that is not always positive or negative. For any x that's smaller than 1, you're getting a negative cubed, which means we're negative. For any x larger than 1, we're getting a positive. But this x and the whole interval, starting just to the right of 1, going up to 2.9 and past 2.9, is all positive. So I would say something like f double prime of x is greater than 0 for any x that's greater than 1. Just showing them you know what the heck you're talking about. So that we're going to go ahead and actually answer the question, right? And our question is L of 2.9 is an, well, I don't actually know, concave up, greater than 0, something like this. Think about your tangent lines. Tangent lines are below. So L of 2.9 is an under, because the tangent line is below, under approximation for f of 2.9 because f double prime of x is greater than 0 for x greater than 1, and so f of x is concave up. We'll say around x equals 2.9. There's probably a better way to phrase that, but I think they'd get the idea. Nifty. We should probably see if we're right, huh? I always hate doing this and getting the wrong answer. So let's go ahead and graph this equation. Let's also figure out the value for f of 2.9. And then let's make sure that our tangent line was less than or greater than, so 21 over 40. So here we go. We're going to go ahead and get rid of this weird square root guy. We're going to graph our equation. F of x equals 1 over x minus 1. There's that guy. They're asking us to write a tangent line at 3. So we had our L of x equals, and it was negative 1/4 x minus 3 plus 1/2. That's looking good so far. Pretty darn tangent. I'm proud of us. And then look at this graph. Isn't this graph concave up here? Looks pretty darn concave up. My tangent line is below, so I think part C looks pretty good. Let's double check my tangent line. Can I actually do L of 2.9? You're going to yell at me. Oh, you did let me do that. That's so nice. 0.525, change it to a fraction, 21/40. Look at that. I wonder what f of 2.9 was. How close were we? What do you mean? Oh, there's something else called f, isn't there? Okay, let's just plug this in then. 1 divided by 2.9 minus 1, 0.52, no more fractions. 525, 526. Oh yeah, they are crazy close to, which isn't a shocker because 3 is really close to 2.9. So we were tangent at 3 and we asked about a value at 2.9. Cool. I'm going to help you guys set up 2A, and then I think you guys will probably figure out the rest of this. It's nothing too bad. I want to check my time, see how long this is going. Yeah, so I think, yes, I can see the window. Thank you for asking. I think, yeah, I'll help you with the setup here, and I don't want to go over, 60 minutes. That takes forever. So the rest of these are really not that bad. It's set up a tangent line, interpret your answer with correct units, and I will, of course, post solutions for this on Teams. Here we go. Create a linear approximation to find each value without a calculator. So we want to find the square root of 16.2. Well, we need to create a linear approximation here. And so our linear approximation, L of x equals, and we know it's going to be like f prime of something times x minus something plus f of something. Now, seeing the square root up here, I'm pretty convinced that I'm going to use the function f of x equals the square root of x. And I'm also pretty convinced I'm not going to do a tangent line at this value because I'm going to need to, imagine if this was 16.2, I'll just show you and then erase it. In order to get a tangent line, I'd have to calculate f of 16.2, and I don't know how to do the square root of 16.2 without a calculator, so I think we'd be out of luck there. Instead, let's pick a number that's really close to 16.2 that I do know how to calculate the square root of. 16, anybody? So let's go ahead and show that we know how to find the square root of 16, which is of course 4. So I'm going to set my tangent line at an x value of 16 instead of 16.2 because we know the output. Also, earlier on we found this derivative. The derivative is 1 over 2 square root of x. So I'm going to find the derivative at 16 as well. 2 times 4 is 8. So that gives me, oh, and I wrote f of 4. That was silly. So this gives me 1/8 plus 4 at the end. Great. Linear approximation. This is tangent to square root at 16, because 16.2 is so close to 16, I think we can use our linear approximation to approximate the square root of 16.2. So the square root of 16.2 is approximated by the linear approximation of 16.2, which is 1/8. Sorry, I should have zoomed in. 16.2 minus 16 plus 4. 1/8. This is 2/10, right? Something like this. Plus 4. Reducing some fractions here, we get 1/40. Let's come up a bunch. Plus 4, which is 4 and 1/40. So I'm suggesting that 4 and 1/40 is pretty darn close to the square root of 16.2. One last check, and then you guys are off on your own for the rest of this. And so I'm just going to quickly pull this up. We have the, oh, go away, shoo, shoo, shoo. We have the square root of 16.2. That's 4.04. And then we have, what was the other one? 4 and 1/40. 4 plus 1/40. 4.025, 4.0249. Oh yeah, we crushed it, guys. You guys are doing awesomely. Okay, so the rest of this is on your own. You have plenty of background to get this done. This is a cube root function, so be careful with that. It's not going to be f of x equals the square root of x. It's f of x equals the cube root of x, and you'll need to pick a cube root that's pretty nice, and the rest of these aren't too terrible. Check your answers at the end. Thank you for hanging out with me, and we are done for the day.